All right, so new screen. For example, let's do a couple set with finite cardinality first. So for example, let's say that x, oops, now my mouse is pink. I don't really want to do that. X equals the set 1, 2, 3, 4, and y equals the set A, B, C, D. X is 1, 2, 3, 4, y is A, B, C, D. Obviously, X and Y are going to have the same cardinality, right? Obviously, we know this, we can count. But if we're going to prove this, we need a bijection. So we can say that the cardinality of X equals the cardinality of Y because F going from X to Y is a bijection where F is given by, and we can do this however we want. So either ordered pairs or arrow diagrams are both completely and totally legal, right? Those are both ways of doing functions. So maybe we'll do an arrow diagram. We could do a set of ordered pairs as well, but arrow diagrams work just as well. So we've got 1, 2, 3, 4. We've got A, B, C, D. We've got F. I'm going to fill in arrows. You can fill in arrows however you want. Make sure that you fill in arrows to get a bijective function. So however you want to do arrows, yours don't have to match mine, but you want to have one arrow going to one point. So maybe we'll do 1 to B, 2 to A, 3 to D, and 4 to C. Again, yours can look like whatever you want. Doesn't matter as long as you have an injective function, or a bijective function, sorry. Bijective function. And with an arrow diagram, it's super easy to tell that we have a bijective function. Easy, give me a thumbs up. That one's easy, no problem, good, okay. All right, let's make it more interesting. Finite sets are boring. So it's super easy to tell whether you have the same cardinality with two finite sets. Let's look at infinite sets. When we're doing infinite sets, we can't do arrow diagrams because there's no possible way to write out all of the elements in the set. We can maybe use an arrow diagram to help us try to figure out what our rule is going to be, but we have to go to a rule in order to prove that a function is a bijection. So let's do first the example that Grace asked about. So let's say that X is the set of all integers and Y is the set of all even integers. So X is the set of all integers, Y is the set of all even integers. It actually turns out that the cardinality of X and the cardinality of Y is the same. So what this means, and this is where you're not going to like me, is that there are the exact same number of integers as there are even integers. They're the exact same number. This is what you don't like. The exact same number of integers as number of even integers. And you're gonna like things even less on Wednesday when we get there. So let's draw an arrow diagram to help us try to figure out what my function is going to look like, and then we can come up with a rule. So we've got the integers over here, 1, 2, 3, 4. We've got the even integers over here, 2, 4, 6, 8, right? This is not an exhaustive arrow diagram. I can't get all of them in here. But what seems to make the most sense is just go straight across. 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8, etc., right? This is not a proof. This is the scratch work before I am doing a proof to try to come up with my function f that is a bijection. So my function is going to go from the integers to the even integers. I am going to take as input a little x based on my arrow diagram here. I'm sending 1 to 2, 2 to 4, 3 to 6, 4 to 8. So x is going to get sent to 2x. Does that make sense? That's my function that I'm claiming is a bijection. Okay, all right. I need to show that f is a bijection. So I need to show that f is a bijection. That's what I need to do in order to finish up my proof. So I need to show that f is 1 to 1 and that f is onto. start writing. I'll start writing. I'll talk a little bit, but you should be able to show both of these. This is actually a good review for the homework that is due on Wednesday. So see if you can do injective and surjective for both of these, integers to the even integers. Injective should be nice and easy, no issues there. Injective should be easy. In this case, I'm getting people nodding at me, that's good. Injective. Surjective, scratch work over here, right? We need f of a to equal b. So we're gonna have a equals b over 2. We're dividing and we're working with integers, so we have to be careful when we're dividing, but remember that b is an even integer. So since b is an even integer, I'm allowed to divide by 2. I'm not allowed to divide by anything else. I can't divide by like 3 or 4 or something like that. That would cause me problems. But I am allowed to divide by 2 because b is an even integer. So therefore, my pre-image is going to be b over 2. And that gets me my surjective part. Okay? All right. Doing good? Making sense? Good review of injective and surjective. So Grace, this should answer your question. Does it make you crabby? You're allowed to say yes. Does it not fit with what you're anticipating? There are exactly the same number of integers as there are even integers. Totally the same number of integers as there are even integers. Okay, let's do the next one. So we also can say there are exactly the same number of positive integers as there are integers. So x is going to be the positive integers and y is going to be all of the integers. There are exactly the same number of positive integers as there are integers. So in this case, the cardinality of x is also equal to the cardinality of y. So here's what I need. I need a bijection. So we'll go 1, 2, 3, 4. And I'm going to do some dots. So we'll go like this over here. We'll put 0 in the middle, and then we'll go -2, -1, 0, 1, 2. I don't really need 3, so we'll stop there. Whoops, that's not what I wanted to do. 1, 2, and then we'll do some dots. So again, this is not a proof. This is not a proof. This is just, let's see if we can come up with a rule and see what happens. So here's what we're gonna do. We are gonna kind of crisscross back and forth. 1 is going to get mapped to 0. 2 is going to get mapped to 1. And then 3 is going to get mapped to -1. 4 is going to get mapped to 2. We'll put one more in here. And 5 is going to get mapped to -2. And then we could keep going. So we're going to be able to crisscross and kind of go in both directions simultaneously. If we just did 1 to 0, 2 to 1, 3 to 2, etc., then we'd leave out all the even or all the negative numbers, and that would not work. That wouldn't give us a bijection. But if we crisscross and go back and forth, we're going to be able to hit all of the positive and the negative numbers. Here's your technical function. It's a little complicated. So f is going to go from the positive integers to the integers. It's going to take an element x and it's going to send it to one of two things. So this is a piecewise function. It's going to send it to x divided by 2 if x is even. So let's look at our even numbers and make sure this works, right? X divided by 2 if x is even. So 2 is even. That means that 2 should get sent to 2 divided by 2, which is 1. It does. That's good. 4 is even. So 4 should get sent to 4 divided by 2, which is 2. That's good. It also does. And then this is the more complicated part. Odd numbers get sent to negatives, and we want to do negative x minus 1 over 2 if x is odd. So negative quantity x minus 1 over 2 if x is odd. And again, we're working with integers, so we got to be really careful with division, but we're okay in this case. X is even means that I can divide by 2. No problems there, right? X is even means I can divide by 2. X is odd means that x minus 1 is even, and then I can also divide by 2, and I'm good to go there. So let's check our odd numbers. 1 should go to 1 minus 1 over 2, negative, that's 0. 1 goes to 0, that's good. 3 should go to 3 minus 1 over 2, negative, that's negative 1, that's good. 5 should go to 5 minus 1 over 2, negative, that's negative 2, that's good, that works. So this is the rule that we have depicted in an arrow diagram on the other side. I won't prove this because it's a piecewise function and we aren't going to do proofs of piecewise functions being bijective, but it turns out that f is in fact bijective. I'm not sure if there's a proof in the book or not. I'm just looking here, give me a second. If there's a proof in the book, there exists a bijection. No, they just tell you that there is. So, all right. So therefore, again, this is one you're not going to like, but it's totally mathematically true. There are exactly the same number of positive integers and overall integers. It feels like there should be half as many, right? It feels like there should be half as many positive integers as integers, but there aren't. There are exactly the same number. They're exactly the same number. All right. Questions on that before we do a non-bijective example, the hard one? Anything for questions? Okay.